Oswald-Walker method. First of all, you'll have to know what is Oswald-Walker method meant for. So, Oswald-Walker method is meant for finding out the relative lowering of vapor pressure of a solution. So, a method applied for finding relative lowering of vapor pressure of a solution. So this is a method which is used for finding out a relative lowering of vapor pressure of any solution, right? Generally, we consider, as far as solutions are concerned, we consider a solution formed by a liquid solvent to which a non-volatile solute is added, right? So generally applicable for a solution, right, which is formed by a liquid solvent to which a non-volatile solute is been added, right? Now, we will, first of all, once again, you have to know that this, when I talk about relative lowering of vapor pressure, let me remind you that relative lowering of vapor pressure is a colligative property, right? So this is a colligative property, and it is not the vapor pressure, but it is relative lowering, which is a colligative property. And this colligative property is generally used for finding out molar masses of unknown solutes. So ideally, why do we measure relative lowering of vapor pressure? We measure relative lowering of vapor pressure of a solution in order to know in order to find out the molar mass of the unknown solute which is dissolved in that solution, right? Now we would have a look at the apparatus, and then I would tell you how to find out the relative lowering of vapor pressure. So look at this. This is, one of the apparatus is used for, finding out the relative lowering of vapor pressure of any solution. Now this is, I have drawn this in a very, very simplified manner. So what do we have here? We have two bulbs here, right? And they have been connected through pipes. Ideally, the entire apparatus, right, and the entire experiment which is carried out is, carried out at constant temperature. So I may write here, T remains constant, right? So this is a very important part here, that T should remain constant here, okay? Now, you can see that dry air, you can see that there is this dry air which is made to pass through this first bulb. This first bulb has solution in it, which means the solvent plus there is solute added to it. And it has been pre-weighed. So mass of this solution inside, or the weight of this solution inside, is known, and it is pre-weighed, right? And this is another bulb which is connected to it. Again, this bulb has only solvent, and once again the weight of solvent is also known, right? So before commencement of experiments, we know the weights of solution and the weights of solvent here, right? And you can see that dry air is passed through the solution bulb first, and then it is made to pass through the solvent, and eventually it goes to the drying tubes. Now here, so we have drying tubes here which would collect any moisture that we get. Ideally what we do is we have, the solvent that we select here is water, right? And even here this is water, right? So this is a solution in which the solute is dissolved in water, and here also we have pure water taken, and you find that here we have some drying tubes, and they would collect any amount of they would collect any amount of moisture that is present in the air as it passes through them. So this is the apparatus, and the two bulbs are also connected with each other, right? Now let us understand what happens here when dry air is passed. Now as you can see that there is this apparatus shown, and you can have you have this dry air which is made to pass through this first bulb, and then it is made to pass through this second bulb. First bulb has solution and the second bulb has solvent. Let us assume that the solvent used here is water. So I'm going to put this as, this is, let's say, water, right? And therefore this is all the solution here. The solution here will have water in which some non-volatile solute is added, right? So this is an aqueous solution of a non-volatile solute, and this is pure water. Now you know that at temperature T, there would be a definite amount of water vapors which would be formed here, and the pressure exerted by water vapors in the first bulb, let us call this as PS, which is the vapor pressure of solution. And there would be vapors here as well, water vapors here as well, and the pressure exerted by the water vapors formed here, let us call this as PO, which is the vapor pressure of pure water at temperature T, right? So we have everything set now. Now let us understand one thing, that as the air is passed through this bulb here, first of all, let us assume that there is only solution here and there is no solvent here. So there is only one bulb. Now when dry air is made to pass through a solution, it would carry with it some water vapors, and therefore the weight of this bulb would decrease. The decrease in weight of this bulb would be directly proportional to the vapor pressure of the solution here, right? So if this bulb would have been alone here without this bulb, then the decrease or the reduction in the weight of this bulb would be directly proportional to PS. In the same way, suppose we had only this bulb, not this, but only this bulb, right? And if dry air would have been passed through this bulb, right, it would have carried water vapors, right? And therefore the weight of this bulb would have decreased. Now the decrease in weight of this bulb would be directly proportional to the vapor pressure of pure water at temperature T, right? So this is like, if this would have been alone, the decrease in weight of this bulb would be proportional to PS. And if this would have been alone, right, and dry air passed through it, the decrease in weight of the bulb would be directly proportional to PO. You know that here, dry air has a fixed capacity of holding water vapors. So now, when dry air is made to pass through the first bulb here, right, it would collect some water vapors. The weight of this bulb decreases, and the decrease in weight of this bulb is proportional to the vapor pressure of solution. So here we say loss in weight of solution bulb is proportional to PS. All right. Now, after taking up some water vapors from here, the dry air then moves into this solution, right? Now, dry air already has some water vapors with it. It is actually supposed to collect water vapors which would be proportional to PO. It is actually supposed to collect water vapors which are proportional to PO, but it has already got water vapors corresponding or proportional to PS. So it already has water vapors which would be proportional to this vapor pressure of solution. So from here, what would it collect? Now here the loss in weight of solvent bulb should be proportional to PO minus PS. Very simple to understand that it should have collected PO from this bulb. But it has already collected vapors which are proportional to PS. Right? Ideally, it should have collected water vapors proportional to this pressure, PO. But it has already got water vapors in it which are proportional to PS. So what would it collect from this bulb? It would collect, water vapors which would be proportional to PO minus PS, because this is already, present in that air. So loss in weight of solvent bulb is proportional to this, right? So that's very simple, right? And therefore, now we can go forward with this, and we can even put this as, I can probably put this as W1 for loss in weight of solution bulb and W2 for loss in weight of solvent bulb, right? Therefore, now I can write W1 proportional to PS and, W2 which is proportional to P0 minus PS. Now, if you understand what is relative lowering of vapor pressure, it is very clear that here we have relative lowering of vapor pressure is given by P0 minus PS upon PO. This is what we get. This is relative lowering of vapor pressure. Now here we can, in terms of loss in weights of these two bulbs, we can put it like this, that this is equal to P0 minus PS. What is it equal to? W2. And what is P0? P0 is nothing but W1 plus W2. P0 is nothing but W1 plus W2. Why? Because W1 plus W2 would be proportional to PS plus PO minus PS. So if you cancel this out, it is PO. So now it is very simple to understand that this is what we have. This here this is our equation, and you know that this here is nothing but your relative lowering of vapor pressure. So basically it is very simple to understand that this is like loss in weight of solvent bulb, and this is like the loss in weight of solvent bulb plus the solution bulb. And this allows you to calculate by finding out experimentally the losses in the weights of solution bulb and solvent bulb, and putting them in this form, you get relative lowering of vapor pressure. So this is the Oswald-Walker method. Now I'm going to solve a numerical with you, so that and here in that numerical we will be using this formula so that you understand this better. So look at this now. As you can see here, that there is a current of dry air which was bubbled through a bulb containing 26.66 grams of an unknown organic compound. So this is our unknown organic compound, and we have to find out the molar mass of this compound. It is taken in 200 grams of water. So this, the dry air was first passed through this solution containing 200 grams of water and 26.66 grams of organic compound, which is unknown. Then the same dry air, containing a little bit of moisture from this, right, was allowed to pass through a bulb containing pure water, and then finally through a tube containing calcium chloride. So calcium chloride would absorb all the moisture that the dry air has carried along with it. So the loss in mass of the bulb containing water was this, right, which is like loss in mass of solvent bulb. We generally put it as W2, and it is proportional to P0 minus PS, you know that. And the gain in mass of CaCl2 was this. Now this is the total amount of water which is collected here from both the bulbs. So I may say this represents W1 plus W2, right? And this here represents the loss in weight of solvent bulb, which is W2. So now I can very easily put this P0 minus PS upon P0, which is nothing but it is W2 upon W1 plus W2, and this is nothing but 0.087 divided by 2.036. I hope this is absolutely clear to you all, right? Now what? You know that P0 minus PS upon P0 should be equal to N2 upon N1 plus N2. Now here we could probably approximate, and we may, because this is not a very dilute solution. 26.66 in 200 grams of water is not a very dilute solution. So this kind of approximation, if you have to do, you will have to, we normally approximate this as N2 by N1. But this kind of approximation, this can be given only for dilute solution. But this doesn't seem to be a dilute solution, so we will have to use the full formula that I have given here. So we would be using this formula, right? So now we have 0.087 upon 2.036, which is equal to N2 upon N1 plus N2. To simplify this, can we do one thing? 2.036 upon 0.087 should be equal to N1 plus N2 upon N2, which is nothing but N1 by N2 plus 1. So can we do one thing then? Can we do one thing? What we could probably do is we could probably have 2.036 upon 0.087 minus 1 is equal to N1 by N2. So we would further calculate this. So here we could probably keep 2.036 divided by 0.087 minus 1. If you calculate this, you generally get a value equal to 22.4, and this should be equal to N1. N1 is like the weight of solvent upon molar mass of solvent, and N2 is W2 upon M2. Now here, this is like N1 is for solvent. We have taken 200 grams of water divided by 18 into molar mass of solute upon weight of solute is 26.66. So now we could calculate and get the value of M2. Therefore, M2 should be equal. M2 comes to around 54 grams per mole. Now this is your answer, and this is how you find out molar mass of unknown solute. So this is one application of our the theory that we did, Oswald-Walker method. This is one of the numericals based on that. So, thank you.